Hi everybody, and welcome back for Unit 4, Notes 4.1. This is actually our quadratics unit, and it will take us all the way from today until winter break. Holy Toledo Batman, but we are going to make it through. This is actually one of my favorite units. There's just a lot of fun stuff in it, and it's pretty straightforward, so if you'll hang in there with us, we'll get through it and you will come out the other side much more knowledgeable about quadratics than when you entered. All right, let's get started. Okay, before we actually dive into quadratics, we are going to look at two different ways to express domain and range that you may have touched on before in your Algebra 1 class, but you didn't spend a lot of time on it. And that's the inequality notation and the set builder notation. Now, up until this time, we've been dealing a lot primarily with interval notation. And that's the notation you're going to use as you go higher and higher and higher in your math class. You're going to see that interval is far more widely used than the other two. However, we do require that you know the other two so that way if you come across it in a future class, you do know what they're talking about and you can easily convert it back to interval notation or from interval back into any of the other forms. Okay, so here's how we look at inequality notation. So for the domain, we know the domain is the set of all x's. So you will notice that x appears in the middle of the compound inequality, okay? So, of course, I didn't put it here, but you would technically have x all in between the inequality signs. Now, you'll also notice that x is nestled in between the lower bound and the upper bound. Sometimes you'll hear it referred to as the left bound and the right bound, but just know left bound, lower bound, smallest value, upper bound, right bound, largest value. So what you're going to do is you're going to squeeze x in between the smallest value of your domain and the largest value of your domain. Now, if you look here at the slide in front of you, you'll notice that I've given you all the different kinds of combinations of inequality symbols you could have. You could have two strictly less than. You could have less than or equal to and a less than or equal to. You could have a less than, then a less than or equal to, or a less than or equal to and a less than. These are all the different combinations, but what you will notice is that they all point to the left, okay? That's why we have the lower bound on the left and the upper bound on the right. Now, for range, same idea. It's always y in between the inequality symbols. You'll notice that the lower bound is still on the left, the upper bound is still on the right. And again, I've given you all the different kinds of combinations that you could have for less than or equal to, all that. But just know that if it's range, it's y in the middle. Now, you're going to use the less than or equal to symbol if the bound is included. Like, for example, think about we just finished absolute values. So we had a bracket around 0. Okay, we had a bracket around 0 for the range because that meant we could actually touch 0 on our graph. It was a touchable piece of the graph. Okay, so if it helps you think about it, use less than or equal to if the bound is included. This would be something where you would use a bracket instead of a parentheses. So if you're going to use a bracket instead of a parentheses, well, in inequality notation, you're going to use a less than or equal to, okay? You're going to use a less than if the bound is not included, okay? So strictly less than, okay? That would be where we would use a parentheses, okay? So strictly less than is where you would use a parentheses, such as infinity or negative infinity, okay? And it's the same for upper and lower as far as which symbols you use when. So if you would use a bracket in interval notation, you're going to use a less than or equal to. If you would use a parentheses, you're going to use a strictly less than. And we'll look at some examples. I just want to get the basics out of the way. Now, before we jump into our examples, we're going to go ahead and introduce you to set builder notation because, guys, it is essentially the same as inequality notation. It just has a little twist. It's kind of like inequality notation with a little flair, okay? So let's look at this. This is the proper form. When we're talking domain, it's basically, check this out, it's inequality with just some stuff around it, okay? So basically, when you're writing the domain, you're just going to add an X slash and birdie braces on either end. Okay, yes, I know they're called braces, but birdie braces is so much like, I don't know, cuter, but whatever. Okay, so you're going to do birdie brace, X slash inequality notation, close those birdie braces. So what I've done is I've given you an example below to show you. So here would be your inequality notation. And again, you put X slash because domain is X's. So, but let's look at how that's actually read, okay? Because you're not going to say birdie brace X slash inequality notation, okay? There's a proper way to read this, okay? So it is read as the set of all X's such that X is greater than or equal to 2 and less than 5. So you're probably like, what? Okay, so let's break that down a little and we're going to go piece by piece. So the set of is what the birdie braces are for. Okay, the set of all X's such that, because the slash means such that. So the set of all X's such that X is greater than or equal to 2 and X is less than 5. So it's not too bad when you break apart the parts. Now let's look at the range. The range is the same way, except instead of X slash, you got a Y slash, because range is the set of all Y's. So I've given you an example below. So let's look at how it's read. Okay, the set of, that's your birdie braces, the set of all Y's such that Y is greater than or equal to 8 and less than or equal to 10. Okay, so that's set builder. Now we're going to look at some examples. Okay, now I'm going to be honest with you guys. It is far easier for me to start with interval notation, then change it to inequality notation, and then change it to set builder. Interval for me is always easier to start with. So let's do the domain here. So we've got a domain that goes from 2 to 9. 2 is not included, might be like an open circle or something, but 2 is not included, but 9 is, hence the parentheses in the bracket. So when I convert this to inequality notation, it's going to look like this. So my smallest numbers on the left, 2. My largest values on the right, 9. And here's how we derive the symbols, because X is in the middle, because it's the domain. Okay? So 2 has a parentheses. So that's why we used strictly less than. 9 had a bracket. So that's why we use less than or equal to. You want to try that again? Let's go over it one more time just to make sure we fully understand. So our domain is from 2 to 9, where 9 is included and 2 is not. So I put my X in the middle. That's all. I would always start there. Put your X in the middle. Put your smallest value on the left, which is 2. Put your largest value on the right, which is 9. Now, to derive the symbols, I used a parentheses around 2. So that means strictly less than. I used a bracket with 9. So that means less than or equal to. Now, in terms of set builder, all I'm going to do is I'm going to take that inequality notation, put an X slash in front of it, put some birdie braces on either end, and you're in set builder notation. So it looks like that. That's why it's always easiest for me to go from interval to inequality to set builder. Because from interval, you make the inequality. From inequality, you just slap an X slash or a Y slash on it, put some birdie braces on it, and you got set builder. Let's look at one more. The range is negative infinity to infinity with parentheses because we all know Buzz Lightyear lied and we can never go to infinity and beyond. Okay, so we use parentheses. So it's range, so there's going to be a Y in the middle. And then you're going to have negative infinity on the left, positive infinity on the right, and you're going to use strictly less than's because we use parentheses. Now we're going to convert that inequality to set builder. All we have to do is smack on a Y slash, put some birdie braces on it, and check it out. Set builder notation. Okay, what I want you to do is I want you to pause the video. I want you to try to complete the next two on your own. When you're ready to check your answers, hit play, and then we'll show you the answers. All right, that's what I got for inequality. That's what I got for set builder. For range, that's what I got in terms of inequality notation. And that's what I got for set builder notation. So see, it's not so bad if you start from interval. Again, start from interval, go to inequality, and then go to set builder. All right, let's move on. Okay, so there are three forms of the quadratic equation. Okay, there are three forms. The first form, that's the easy one. That's the parent function. That's what we studied back on 3.1. There's standard form, y equals ax squared plus bx plus c. Probably looks familiar from doing the quadratic formula. And then we've got vertex formula. So just like we had the parent function in Unit 3, and then we had the vertex form, or the transformational form, that's the same thing in vertex form. So we've got parent function, y equals x squared. We've got standard form, and then we've got vertex form. Now, today we're going to be focusing on the vertex form. Remember, this is simply moving it left, right, up, down, stretching, shrinking, reflecting over the x or y axis. So it's basically everything we did back on day 3.3. It's just a different parent function. Now, there's something else we want to draw your attention to. There's something else we want to draw your attention to. And that is this little lime green box right here. You are going to hear us say solutions, roots, zeros, X-Intercept. Solutions, roots, zeros, X-Intercepts. Those are going to be referred to shorthand notation as SRZs because essentially they are the same thing. SRZs, solutions, roots, zeros, are the same thing as X-Intercepts. So just know when you hear that, we're really talking about X-Intercepts. We're talking about where our graph crosses the x-axis. Okay, let's talk about transforming the quadratic function. Now you'll notice that this table is very similar to the one you wrote down for absolute value. And that's because it's exactly the same one as you wrote down for absolute value. The only thing that's really changed on this slide, or that will change on each function, is the equation at the top. So instead of being the absolute value function, it's now the quadratic function. And also the domain and range might change. But other than that, everything else is still the same. Okay, so you'll notice that B and H, they're still inside the function. But now what that means is they're inside of the function, the part that's being squared. So you'll notice that that bracket is being squared and B and H are inside of that. It's still opposite day. They're still going to affect the x's. You'll notice that A and K are still on the outside of the function. You still do that at face value. You do what it says, and it affects the y's. Okay, so that hasn't changed. The vertex, it's still going to be HK. The axis of symmetry, we talked about that briefly in absolute value. If you'll remember, the axis of symmetry is that imaginary line that it's vertical that goes directly through the vertex. So it's x equals h. PEMDAS is still going to tell us we have to multiply before we add or subtract. Okay? The domain of a quadratic. Well, the domain of the quadratic parent function was negative infinity to infinity. Okay? That hadn't changed. It's not going to change no matter how we move it up, down, left, right, stretch it, shrink it, reflect it, all that stuff. Okay? Not going to change. Still going to be negative infinity to infinity. Now the range. This is going to remind you of the absolute value. Okay? If A is positive, it's going to open up. So my range will be K to infinity. If A is negative, it's going to open down. So your range is going to be negative infinity to K. It's just now, instead of being a V-shaped graph, it's a curve, and you've kind of got that bowl shape down around the vertex. So it makes a curve instead of a V. We also put on here, just for your reference, to find the x-intercept, you put in 0 for y, which we knew, and the y-intercept, you put in 0 for x, which we also knew. So again, this really hasn't changed, and it's not going to change from function to function. Really, the only thing that's going to change, again, is the equation and the domain and range. So let's review the quadratic parent function. We know that that is -2, -1, 0, 1, and 2. Those are our Fab 5. And this time, though, our y's are 4, 1, 0, 1, 4. So when we plot those 5 points, it makes a curve. It's supposed to look like a curve. The graphing tool had other ideas, but it is a U-shaped curve. Okay? The domain of the parent function, still negative infinity and infinity. That hadn't changed. The range is 0 to infinity, but 0 gets a bracket because we can touch 0 on our graph. The x-intercept is 0, 0 because it's at the origin. The y-intercept is 0, 0 as well. Now, your vertex is at 0, 0. And remember, we talked about the axis of symmetry being that kind of invisible line that cuts your parabola in half. Okay, so that kind of would be your axis of symmetry. That's x equals h. Well, remember, the h is the x coordinate of the vertex. So x equals h, that means it's going to be x equals 0. So that's just a quick reminder of the parent function. Okay, let's graph a function. They want us to graph y equals x minus 2 squared plus 1. Well, the first thing I always start out by doing is you should always start by writing the parent function table. Trust me, guys, I've been teaching this forever, and if you start off by writing the parent function table and you create your new table, it's going to make it so much easier on you. Okay, so we start by writing the parent function table. Now, how am I going to go from old x's to new x's? Well, remember, b and h affect the x's. They're inside the part of the function that's being squared. My b value is 1, so no effect on the graph. But I do have x minus 2. Well, remember, to go from old x's to new x's, The function says to subtract 2, but it's inside the part that's being squared. So that's opposite day. So what's the opposite of x minus 2? X plus 2. So we are going to add 2 to every single one of our x's right here in the x column. So negative 2 plus 2 is 0. Negative 1 plus 2 is 1. 0 plus 2 is 2. 1 plus 2 is 3. 2 plus 2 is 4. Okay, so we've got all of our x values. Now let's talk about the y. There is no a value, so we don't have to worry about that. But I do have a 1. That's my k value. So k's affect the y's. So I'm going to add 1 to every y value. So I get 5, 2, 1, 2, 5, because 4 plus 1 is 5, 1 plus 1 is 2, 0 plus 1 is 1, 1 plus 1 is 2, 4 plus 1 is 5. Okay, now that's what it looks like graphed. All right, so you can see the curve, you can see the bowl around the vertex. Let's talk about the transformation from the parent. Well, x minus 2, that 2 means left and right movement, so it's x minus h, so that means I'm going to go right 2. The 1, that's your vertical movement up and down, so I'm going to go up 1. So the transformation would be right 2, up 1. All right. Let's see if we can find these values. Well, our domain, that's still going to be negative infinity to infinity. Our range, well, our range is, it opens up, so that means it's k to infinity. Our k is 1, so it's 1 to infinity. X-intercept, there are none. I don't cross the x-axis, so there are no x-intercepts. Now that leads me to this next question real quick. Are these solutions, roots, and zeros real or imaginary? If I don't have any x-intercepts, are the solutions, roots, and zeros real or imaginary? And the story behind that is they're imaginary. Because if a graph doesn't have any x-intercepts, you're not going to have any SRZs that are real. So they're going to be imaginary. And if you were to multiply this out and get it in standard form and do the quadratic formula on it, you would discover that that produces that negative underneath the radical, underneath that square root. So when you're imaginary and you do the quadratic formula, you end up with the negative underneath the square root part of the quadratic formula. So the y-intercept, I can tell I have across the y-axis at 0, 5. The vertex, that's my h and k, and it's also on the graph as 2, 1. And then the axis of symmetry. Now, remember, the axis of symmetry is, I'm going to erase that because that is not writing right. Okay, so the axis of symmetry is x equals h. All right, x equals h. That's the formula for our axis of symmetry. X equals h. All right, so x equals h. Well, our h is 2. So that's going to be x equals 2. Now, if we were to fold that along x equals 2, you'd notice that it produces a mirror image because it reflects over that axis of symmetry. Now let's find the max over negative 2 to 4. Now remember what I told you in absolute values. When you are finding the max and min from this point forward, you're going to have to do f of L, f of h, f of r. F of L, f of h, f of r. We know left and right come from the interval, and then the h, that's the x value of our vertex. So my left is -2, my right is 4, and the x coordinate of my vertex, that h value, that's 2. So I look and I say, well, okay, is 2 between -2 and 4? And it is, so I have to go ahead and calculate it. So what I do is I plug -2 into the equation. -2 minus 2 is -4. -4 squared is 16. 16 plus 1, that's 17. I then plug 2 in. 2 minus 2 is 0. 0 squared is 0. 0 plus 1 is 1. I then sub in the value 5 for x. Or I'm sorry, not 5, 4. 4 minus 2 is 2. 2 squared is 4. 4 plus 1 is 5. So I look and I'm going, okay, I need the maximum value. I need the maximum. Well, the biggest answer there is 17. But remember, we can't just say, hey, 17 is the max. We've got to write it in proper form. Okay, so the proper form is saying, hey, f of -2 equals 17. That's my max. So remember, if you don't write it in the proper form, you're not going to get full credit. Okay, because you've got to demonstrate that knowledge that, hey, my max is 17, but that really occurs at f of -2. Okay, so f of -2 equals 17 is your max. Okay, well, what if I ask you to find the min over -5 to 1? Well, guess what? Still going to have to do f of L, f of H, f of R. So I know my left and right, that's -5, and my right is 1. My h is still 2 because we're still using the same equation. So I look and I say, okay, is 2 in between -5 and 1? No. 2 is not on the number line between -5 and 1. So we don't have to take him into our calculations. We're like, forget you, we're just going to work with -5 and 1. So if I plug -5 in, I get -5 minus 2. Well, that's -7. -7 squared is positive 49. 49 plus 1 is 50. And then if I plug 1 in, 1 minus 2 is -1. -1 squared is 1. 1 plus 1 is 2. So now I want the minimum. That means I want the smallest answer. So that's 2. So I have to write it in proper form. The minimum occurs at f of 1 equals 2. Let's graph another. They want us to graph y equals -2 times x plus 3 quantity squared plus 4. Okay, so first thing I do is I'm going to go to my parent function table and write that down. Then I'm going to say, okay, how am I going to go from old x's to new x's? Well, inside the function, it says x plus 3. But I'm like, no, 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 it's opposite day. I'm not going to add 3. I'm going to subtract 3. So I subtract 3 from every x in the parent function. Then, to go from old y's to new y's, I have this -2 and an addition of 4. Well, I know a and k affect the y's. I also know you do exactly what it says. And I also know that PEMDAS tells me to multiply before I add or subtract. So I'm going to take every y, I'm going to multiply it by -2 and then add 4. So for example, 4 times -2 is -8, plus 4 is -4, and so on. I graph the function. Let's talk about the transformation. Well, that x minus 3, x plus 3. X plus 3, well, it's x plus h. So that tells me I'm going left. I'm going left 3. This 4 tells me I'm going up 4. The 2 tells me I have a vertical stretch of 2. And the fact that it's negative tells me that it's also reflected over the x-axis. So let's talk about the domain. Still a quadratic, so it's negative infinity to infinity. It opens down, so my range is negative infinity to k, with the k being 4. The vertex is at negative 3, 4. And the axis of symmetry goes straight through the vertex. So it's x equals h is negative 3, so it's x equals negative 3. Now, let's talk about finding the max over the interval negative 7 to 5. So that tells me we're going to do f of L, f of h, and f of r. My left is negative 7, my right is negative 5, and this time my h is negative 3. So, is negative 3 in between negative 7 and 5? Nope. So that means I don't have to worry about it. I just calculate negative 7 and 5. So negative 7 plus 3 is negative 4. Negative 4 squared is 16. 16 times negative 2 is negative 32. Negative 32 plus 4 is negative 28. I rinse and repeat with negative 5. So negative 5 plus 3 is negative 2. Negative 2 squared is 4. 4 times negative 2, negative 8. Negative 8 plus 4, negative 4. So surprisingly, my biggest value is negative 4. So I'm going to say the max is f of negative 5 equals negative 4. Now let's try the min. I want the min over negative 4 to 3. Still going to do f of L, f of h, f of r. Left is negative 4, right is 3. My h is still negative 3. This time, negative 3 is in between negative 4 and 3. So I plug each of them into the function, and I get 2, 4, and negative 68. They want the minimum, so the minimum is negative 68. So I'm going to say f of 3 equals negative 68, and that's my min. Now, you'll notice on this that the parabola doesn't cross the x-axis at pretty points, and I'm not quite sure where it crosses the y-axis at. So we're going to have to solve for the x and y intercept. So for the x-intercept, we know that that means y is 0. So we're going to put y in for 0. Now, our goal is just like we isolated the absolute value, we want to isolate the term that's being squared. So we want to get the term that's being squared by itself. So my first step is to subtract 4 from both sides. So I get negative 4 is equal to negative 2 times x plus 3 quantity squared. I now divide by negative 2, and that gives me 2 equals x plus 3 quantity squared. Well, how do I undo squaring something? I take the square root. Now, here's something you need to pay attention to. Anytime you take the square root and you put it there because you're solving, so if you've done the physical act of taking the square root, you have to put plus or minus, okay? Because think about it. If you're solving and you put the square root over the 4, well, that could be positive 2 or it could be negative 2, because positive 2 squared is 4. Negative 2 times negative 2 is positive 4. So you have to take into account both the positive and the negative. So if you put the square root, you've got to put plus or minus on your answer. And then, of course, square rooting the quantity squared just leaves you the quantity. And then we have to solve for x. So I subtract 3 from both sides. Now, I can't leave those as my x-intercepts. I actually have to write them in coordinate point form. But do not, I repeat, do not get the decimal equivalent unless you're told. I want the exact x-intercepts. So my exact x-intercepts are -3 plus the square root of 2, comma 0, and -3 minus the square root of 2, 0. Now, does that mean these solutions are real or imaginary? Well, they're real because I actually physically cross the x-axis. Now, let's talk about the y-intercept. The y-intercept is where we put in 0 for x. Well, 0 plus 3 is 3. 3 squared is 9. -2 times 9 is -18. -18 plus 4 is -14. But we have to write it as intercept form. So that means I'm going to say 0, -14. Now, it wants to know on what interval of the domain is the function decreasing. Well, if you look at the right side of your graph, think about like we talked about with the absolute values, same idea. It is decreasing on the right side. Well, where does it start? Where does your function in your graph start decreasing? Well, it starts decreasing at the vertex. So the x-coordinate of the vertex is -3. So I'm decreasing from -3 to infinity. So the x's where my graph is decreasing start at -3 and then they go to positive infinity. Well, where is it increasing? Well, it's increasing on the left. Well, where does it start increasing? Well, it keeps going all the way down. So it's going to keep going to the left as well. So it's increasing from -infinity to the vertex. Well, the vertex is -3. So it's going to increase from -infinity to the vertex. Let's look at one more. And this time it has a b value. Well, if you remember what I told you back in absolute values, you cannot get h, b, a, k, you can't get any of that until you separate the 2 from the quantity 2x minus 4. You have to factor out the b. It still stays in the quantity squared, but it is no longer part of 2x minus 4. So I factor out the 2. So inside my function, I now have 2 times x minus 2, and that whole quantity is squared. So my a is -3, my b is 2, my h is 2, and my k is 10. I know my parabola, it's going to open down because a is negative. A is negative, so it's going to open down. My vertex, well, remember, you can't get your vertex until you factor out that b. That's another reason why we do it. Your vertex is 2, 10. It's your h and your k. So now we're going to start with our parent function. Okay, so we are going to shift off the parent function. So we start up our new table, and inside the function, I am multiplying by 2. I'm multiplying by 2, and then I'm subtracting 2. Multiplying by 2, and then subtracting 2. But we're smarter than that. It's opposite day inside the function. So instead of multiplying by 2, I'm going to divide by 2, and instead of subtracting 2, I'm going to add 2. So I'm going to divide each x by 2 and add 2. -2 divided by 2 is -1. -1 plus 2 is 1. -1 divided by 2 is negative 0.5 plus 2 is 1.5. 0 divided by 2 is 2. I'm sorry, it is so not 2. 0 divided by 2 is 0, plus 2 is 2. 1 divided by 2 is 0.5. 0.5 plus 2 is 2.5. 2 divided by 2 is 1, plus 2 is 3. Now, to go from old y's to new y's, I'm going to multiply by negative 3 and add 10. Multiply by negative 3 and add 10. So like, for example, negative 3 times 4 is negative 12. Negative 12 plus 10 is negative 2. And so on. So I'm now going to graph the new table. And that's what my parabola looks like. All right, let's do some equation work now. So I want to write the equation of a parabola in vertex form with a leading coefficient of negative 4 and a vertex of negative 5, 3. Well, your leading coefficient is always A. Your leading coefficient is always A. So that tells me that A is negative 4. The fact that my vertex is negative 5, 3, that tells me my H and K. Now, when we're asking you to write equations, we are never, ever, ever, never going to assume that there's a B value. So when you're just writing the equations, you're only going to do A, H, and K. So I'm going to take vertex form, and I'm going to plug in what I know for A, H, and K. So that gives me Y equals negative 4 times x plus 5 quantity squared plus 3. Now remember, it's x minus h, but my h was negative this time, so minus a negative became plus a positive. So that's what we call vertex form. Now, what if I wanted you to switch vertex form to standard form? Well, remember what I've told you about a parentheses squared? Anytime you see a parentheses squared, that means, hey dude, write me twice. Anytime you see a parentheses squared, that means, hey dude, write me twice. So I write x plus 5 times x plus 5 instead of x plus 5 squared. I next am going to multiply x plus 5 times x plus 5. So that gives me negative 4 times x squared plus 10x plus 25 plus 3. I'm now going to distribute the negative 4. That gives me negative 4x squared minus 40x minus 100 plus 3. I now combine any like terms. And so standard form is negative 4x squared minus 40x minus 97. So you're going to want to know how to write the equation given the information in vertex form, but you're also going to need to know how to convert that vertex form to standard form. Let's look at another example. Write the equation of a parabola in vertex form with a vertical stretch of 2, a vertex of negative 4, 3, and a maximum value of 3. So I know my vertex, and I know vertex form, and I know my vertex is HK. So I know my H and my K are negative 4 and 3. A max value. So we know parabolas, they're either going to have a minimum value. Minimum value means the vertex is at the bottom, and so it opens up. Maximum value means my vertex is at the top, and it opens down. So The A is 2, but the maximum value of 3 means that your parabola is going to open down. So if they tell you you have a maximum value, that tells you your parabola opens down. If they tell you have a minimum value, that means it opens up, so A is positive. But if they tell you it has a maximum value, that means that your A is negative. Okay, now this isn't quite the same as the maximum over an interval. So quadratic functions, they have an absolute max or an absolute min. If they open down, you have an absolute max. If they have a min, you have an absolute min. Okay, so absolute max means your vertex is at the very top and it opens down. Absolute min means your vertex is at the bottom and it opens up. Now you can still do max and min over an interval, but again, parabolas have an absolute max and an absolute min. If it's an absolute max, it opens down. If it's an absolute min, it opens up. So since we have a max value, that means it opens down, which means our A is negative. So we have A is negative 2. So then all we do is sub in A, H, and K, and voila, there you go. All right, next example. Write the equation of a quadratic in vertex form with a vertex of 3, 1 and an X-intercept of 4. Okay, you're really going to want to pay attention to this, and you need to know how to do this. You may see this in your very near future. That's all I'm going to say. So you're going to need to really make sure you pay attention to this. We want to write the equation of a quadratic in vertex form with a vertex of 3, 1 and an X-intercept of 4. So we know vertex form. I know I have a vertex, that's my H and K. But guys, this time they didn't give me an A. So we're going to need to use the vertex and the X-intercept to solve for it. So if I have an X-intercept of 4, A, they wouldn't get credit because they didn't write it in vertex form. But my X-intercept is an XY. So I am going to plug in H, K, X, and Y, and I'm going to solve for A. Now, this would be the same if they didn't give you an X-intercept. If they said, hey, you've got a vertex of 3, 1, and you've got a point of 5, 2. You would still do this method the same way. So we're going to take our vertex and our point, and we're going to substitute it into y equals A times x minus h squared plus k. Y was 0, x was 4, h was 3, and k was 1. Now I just simplify. 4 minus 3 is 1. 1 squared is 1. Now the minute you square this guy, the very minute you square him, you move him to the front of A. Guys, I see kids every year, they go, oh, 1 squared is 1 plus 1 is 2. No, it's not. That's 1 squared times A. So you've got to do 1 squared, which is 1, pull that guy in front of the A because he's getting multiplied by A. Don't make that mistake of combining those. Because again, every year they combine these. I'm like, what are you doing that for? What happened to PEMDAS? So you've got to do the exponent, then the multiplication. Okay? So I have 1A plus 1. I'm going to subtract 1 from both sides, and I can drop the 1 in front because it's like redundant. So A equals negative 1. So now I have A, and I have H and K, and I can write my equation. Now, it doesn't matter to me if you say negative 1 in front or just a negative. Either way is perfectly mathematically acceptable. Last example. I want you to write the equation of a quadratic in vertex form that has been shifted left, 7, down 5, vertically shrunk by 1/4, and reflected over the x-axis. Okay, we need vertex for it. Left 7. That tells me that my h is -7 if I went left 7. Down 5, that means k is -5. Vertically shrunk by 1/4 means that a is 1/4, but it was also reflected over the x-axis. So that means a is really -1/4. I then take that and plug it in for a, h, and k, and there's my equation. All right, so that is it. That is it for today. Your homework is worksheet 4.1. It will be due next class or whenever your teacher assigns it due. So 4.1 will be due whenever your teacher has the due date. And that's it. So go work on worksheet 4.1. Wash those hands. Socially distance. Please, people, wear a mask. And please be cognizant of your surroundings. Be careful. Be safe. Have a good one. We'll see you next time.